It wasn't me, so it must have been me.
Yeah. Well, I mean,
I'm not saying there's going to be no curving for people in 100. No, we're saying it for next Thursday.
No, it's not a lot more.
Why do they complaining? It's summer. That's what I do. I canceled like Tuesday and
What time is it?
It's already 12:15.
Can we just read this? Can we just read the outline and go?
Well, it's better if I just go through it real fast, isn't it? And then just sample.
you want it, what you want?
We can't do samples on the board anymore. Can we go to this overhead still? Yeah. So we can do anything. Okay.
Will you go over what homework is due that's left on the syllabus?
Well, yeah, we already did that. Well, you want to skip all the last homework?
Sure.
Yeah.
If you want to do thermal method.
We'll figure it out.
Surely you want your money's worth.
I want my sanity back. Don't put it on yet. We have some private things to discuss.
Well, they're going to be the same though.
Okay, let's not get off of them.
Anybody else want their money's worth, they can have mine.
I can see my reviews.
You can get your money's worth by doing it on your own if you really care that much.
Well, okay. This company called me and wants me just to do it in Word, and they charge people. You don't get college credit with the deviation. You can just go to the internet, pay your money, and just read the Word. And I'm thinking, how do you learn? You don't do homework. You don't take tests. You make you do the work, or you don't learn. You guys don't read the chapter, right? You read it already? Okay, what's thermal method? Okay, what's thermal method? Well, see, it's the homework though that makes you read. That's the only reason you're doing it. Basic human nature is you're not going to do it unless you're Muhammad. Unless Are we on? Are we? Okay, everybody should have 3 chapters. 11, 12, and 13. All right, I'll do 12.1 in class. Let me do those. I'll just show you the answers. And then it's the same as doing it, right?
Are we not doing the final decision no more homework?
No more final. No final exam. What do we think? Take a vote. Who's against doing homework?
I could care less, whichever way.
I don't have time.
You don't even work. You're the one that doesn't work. It depends on your thing. You're going to need some background. No, because let's say you do a biological one, you won't learn how to do incinerate. Yeah, but you won't have practice doing one. I'll do 12.1 in class. Okay, that's a homework problem. 12.1, which you get the idea.
So we have homework for what, 11, 12, and 13?
Still, yeah. And then, but you, wait, I'm looking at the wrong year. Wait a minute. One of my, you did 9. Oh, 10 you didn't do. All right, do 10 and then that's it. The next class, which won't be till the 2nd.
Are we going to do a presentation the 2nd or the final?
I'm thinking the 9th. Let's give us till the 9th. Is that okay with everybody? Instead of the final exam, we're doing presentation.
That's on the final exam day.
What about the paper?
Everything. But only a short presentation, because we're only going to do like 5 to 10 minutes. That means only 5 or 6 slides, Muhammad. Well, I'll tell you. It's just an overview. You're gonna explain your method to everybody else in class. Yeah. Okay, are we ready? I'm not paying us any attention. Okay. Guess I need to load mine.
His name is Jared.
Jared?
Jared Harper.
What are we doing here? How does this one work? Guess you don't have that. Oh, the chunky guy. The subway guy, no? We're always making, Allie's always making fun of that guy.
No.
You guys don't know? Well, he looked a little chunkier, though.
He lost 3.
Very.
He was having fun because he
I think we're on tape, you guys. Let's forget about Jared in this one. I'm personally tired of seeing Jared. They started new commercials where they make it up fresh, this new fresh thing about Subway, so. Got a commercial. Commercial, okay. Oh, that's stupid. Okay. Okay. Okay, students. Business learning students. The in-class students have bad attitudes because they're turning the test in today. So you will hear it. The other ones. The other ones. We have several that are having bad attitudes. And we're having a little bit of a problem. And I just heard from distance learning that you can't see what we write on the board, so we're going to try not to write on the board today. We'll do a problem on the overhead camera if Jared or whatever can do it for us. You're Jared? Okay. He's not the San Jared. He's the other Jared. Okay. So we're going to do 3 chapters today, 11, 12, and 13. Quickly, because students want to go for some reason, go out in the heat. And notice, we're not having class next week, the 26th, so we'll cover the rest of it the next week, August 2nd. So your final exam is your presentation and your paper on the site project, which will be then due on the 9th. So we're going to show the videotapes, and the in-class students will do their oral presentation on the 9th here at regular class time. Jared, hopefully we can have this room at regular class time on the 9th. So that's our final grade there, final exam. So we only have the midterm. Then as far as homework, all we're going to collect from now on is in chapter 10. If you're still going to do it and have questions, come talk to me or we'll do it here. So I would say I'd like you to do the rest of the homework because like the incineration, you might want to give it a try. We'll do one here in class, but it's something to know about how to do it, and you have an appreciation for it. But do read the book because when you do your site analysis, which is the next question, the site paper, I gave you the EPA website on that yellow syllabus you guys are beginning of class, the first day of class. If you go there, there'll be lists of them. They're only 2 pages, though. It's just a short description. But after the description, there are 2 contacts. There's the EPA contact and the site company contact. So you want a project that you can get some operating data on because you're going to tell the rest of the class the description, how it works, and then you're going to find out, get the data, see if it does work, what they said it would do. Then you're going to tell us, would you recommend this? So you're going to act like a project engineer. You're looking at all these alternatives. Does it work? And some of them don't, obviously, and some of them don't. But there's a category you want to get one that has operational data. So you need to start on that as soon as possible because they're not all available on the web. So you're going to have to call people. And so you might pick a couple to begin with and see who you can get the response from because we only have it 3 more weeks. Okay, so it's less than 10 pages, a regular technical paper, so introduction on the process, which you can find on the site report. And then the operating data that you get from the company or EPA, whoever you get. Sometimes they publish the stuff, so it might be actually easy to get an older one. Cost is an important object there. Does it work is the first question, and also cost. Cost per ton of contaminated soil or water, and then flow-through rates, gallons per minute or tons per day or whatever you can get on it. And then, of course, what you think. You're all graduate students now, so you're going to have an opinion. You're going to be out there in industry telling people what to do, which is kind of scary. When people ask me what to do, I'm like, oh, God. But, weigh it from a logical standpoint. Does it work? And from your book, you might find some older technology that might work better, so you might want to compare it. If it's a thermal method and it costs a lot, there may be a simple biological method. So at the end, you might want to see. This might not be the best method. Now, EPA has some other sites that compare things. So if you're lucky enough to find that site, which I couldn't find, that compare technologies. Okay? So the whole reason they do the site, actually the guy on the email for the site webpage was very nice and sent me information, which I gave to you. Did you download it? Because if you look at the appendix, it kind of has, if you have soil that's contaminated with petroleum chemicals, here's what you can use. So there's kind of a comparison if you look at the whole website.
You can pick one doing that way if you don't think.
Yeah, but some people have already said this looks interesting, radioactive soil, and they thought it was interesting. But you can't use anything that your company uses. People at Savannah River, you cannot do anything at Savannah River. The intent here is to learn some new technology. So I don't want, Westinghouse does it, don't pick a Westinghouse thing. We want totally unbiased opinion here. So pick something else and learn something. So again, under 10 pages, double space.
Maybe 5 pages.
If you can get it done in 5. But like I said, introduction on what it is, what it's supposed to do, then operating data. You may be able to get charts. If you have like sites that's been done, stick like maps in the appendices. Some companies will hand you 30 pages, some companies won't. So that'll all be due on our last class, which now is August 9th. Forgot. Anyway, has anybody gotten to the website? It's okay. Okay.
We need to call you and make sure nobody else.
Yeah, I would like to know what you're doing. If you'd email me and send me what you're doing. I just don't want anybody to send. I'm out of town next Monday till the following Monday. I'll be back August. I don't want you doing the same thing. And if you're interested in biological, definitely do a biological one. Just do something you're interested in. It would be nice if you would decide. Like I said, some of the distance learning have already sent it in. They were somehow ahead of us. But who are they? They're very good students. Army Corps of Engineers, Savannah River, somebody at Westinghouse, Anniston, somebody...
Well, they're obviously only taking one class.
But they're also working full-time, Lynn. Let's not get back in that. Positive. You can do whatever you make up your mind to do. You're going to look at graduate school and think it was a really good experience, believe me. Next month. The end of next month. The best time of your life. Really, because, all the other graduate students, you guys are lucky because you're with other graduate students. Distance learning people don't have anybody to talk to, so I feel kind of sorry for them. But graduate school is a good experience, I think. Different than undergrad, where everybody's trying to get through. Oh, okay. Oh, carrots? We're going to have carrots. Okay. Any more questions about the site thing? If you want to send me the draft, just send it to me if you want, you want me to look at it. But just make sure you know how to write a technical paper. Technical, no I's and U's, and no personal pronouns. You would think so, but I've been giving some master's projects. They're horrible. So.
Well, when what we think we have to use items.
Yeah, and your opinion, yeah. On your opinion part. I'll put a section on, yeah, you can put the author, yeah, or the investigator, whatever. What was I going to say? Remember to use references, and you can reference telephone conversations if you have it with the people, or websites or whatever. So remember to use references. As I said, maps you might want to stick in the back, but anything that's pertinent with tables or data you want to put in there, unless it's 200 pages. In the body, you know how to write a table. Table 1, give it a title. It seems dumb, but some students don't even know that, or figure 1. Like I said, some companies are very open, some of them aren't. Sometimes it helps, if you're a student it helps, sometimes it helps if you say you're with a company. It just depends if you think they're going to sell you something actually better. But hopefully we can get that done. So you need an idea in the next couple days. All right. What do I need to do here? Oh, Chapter 11, the stabilization solidification, which is a method I'm not real fond of, but it goes around, so we're talking about it. In fact, I used it at the arsenal here. What is it? It's employing additives to reduce the hazardous nature of the waste, sometimes called fixation, an older word, to limit migration or decrease toxicity. Most of the time it's the first. It's just to make it so it doesn't move. There's no risk if it doesn't get to humans, right? You learned that before. If you don't drink it or eat it or touch it, there's no risk. So they're kind of tied up, bind it up. That's called fixating it. There's another one called solidification, which is adding material that will result in a solid end product, like concrete, which we'll talk about. So there are different ways to do these both, but they're tied together. Y'all heard what leaching is before? You know what leaching is? Okay. Process by which contaminants are transferred from stabilized matrix to liquid medium, which we don't want. Once we tie up this hazardous waste, we want to keep it there in the concrete or whatever for moving. So if it leaches, we have a problem. Okay, what are the advantages? It improves the handling characteristics to make it a solid. Take it out of the barrels or take it from a sludge or a liquid to make it solid. We can move it easier. It decreases surface area in some cases, limit the solubility. If we tie it up, like the fixating part, and it's not soluble in water anymore, acid, it helps us too. And sometimes it reduces toxicity. You can change the actual constituents. And decrease compressibility. A liquid, if we put a liquid in a sponge and you mash it down, what happens? It compresses and the liquid goes, that's not what we want. So obviously we're not going to use sponges, okay? So a compressible thing would be like a sponge. So we don't want to use that. We want to use something that when it compresses, the liquid does not come out. And also we can use it for strength. There are some applications where they've used some hazardous material actually in construction. And if we decrease permeability, we don't have to worry about migration because if it doesn't come out, it doesn't migrate. We have no trouble. So anyway, okay, regulations. The most significant regulation, of course, is RCRA. It says that liquid waste cannot be disposed of in landfills. And that's any kind, like even from your house. You're not supposed to dump oil waste from your car into the regular landfill. So that was outlawed way back in the Hazardous and Solid Waste Amendments of 1984. That's why we don't do it. And one of the tests that they use is the liquid release test, which is like the compressible sponge thing, how the liquid comes out. So there's different tests out there, and we'll go through the tests real quick. But the book has got a real thorough part on the testing. It's usually as a remediation alternative or for residue treatment or used on contaminated land. As I said, a lot of times it's not a treatment, it's just holding it in place. I'm not real crazy about it. Later on, we're going to talk about chapter 13, which is land disposal, which is a little bit different. But before you can put anything in land disposal, you have to stabilize it prior to landfilling. And that's what some things they use sawdust. But remember we talked about the compressibility factor? Sawdust doesn't hold liquids real well. I mean, it pulls it up, but then as soon as you compress it under pressure, it comes out. So that's a bad one. And a lot of times it's got to be chemically and physically bound in the agent, the concrete, let's say. It's got to really be bound in there so it can't migrate out. So those are the most important things. If you're doing site remediation, the stabilization is to decrease migration. It may be more cost effective. And here at the arsenal we did that. There were some arsenic ponds where they put the sludge, contaminated arsenic, in there. And when they tried to clean it up, I don't know, for some reason they decided just to stabilize it or fixate it. And then they kind of covered over rather than removing it and doing something with it. So there are examples where they do it cost, for one thing, and there was no receptor around there. That would have been a problem. The mechanisms are actually, I'll go through all these, macroencapsulation, microencapsulation, absorption, adsorption, precipitation, detoxification. Well, anyway, these are all on your handouts. Microencapsulation is physically entrapped in a larger structural matrix. If the structure is broken down, the pollutant may migrate, which is bad. So we need to do laboratory studies. So if it works, like say the sponge idea, if it works in the sponge, then you have to do the studies to find out if it comes out. So like we were talking about the hair and the oil, you know, hair may work really well, but is it really on there permanently? Can we then dispose of the whole mess? Or now do we have to do something else? Because we stick that in a landfill and the hair gets compressed, is the oil going to come off of it? Okay, and I would assume it's probably adsorption. It's not really macroencapsulation, but I'm not sure. Okay, microencapsulation, obviously small. Macro is large, right? Micro small. It's trapped actually within the crystals of the material. And degradation should not affect migration. If the material, sawdust or whatever, goes away, it'll still be there because it's in the crystal structure, so that's better. Absorption, contaminants are taken into the sorbent itself, like a cotton. They're used to remove the free liquid. Fly ash is used, soil, kiln dust, clay materials. Now we were talking about the kitty litter thing. Sawdust, hay straw, other things. Some of these, again, are not good because they're not stable. Adsorption, we talked about that. It was a whole different chapter, but it's electrochemically bound to stabilizing agents. Remember, on the surface is what adsorption is. Modified clays are organophilic. They like organics. So we can use that. If they like organics, let's attach organics onto the clay, and they tend to hang on to it chemically. So clay is good for that, unless you want to clean the clay. We have a contaminated site here at the arsenal, and it is clay. It's hard to get it out of the clay. Okay, the technology, as I said, there's been around for a while. The first thing that they used for this was cement, regular Portland cement, because it makes a solid, right? Use the Portland cement, you do an admixture, sand or rocks or whatever, and water, and it forms a solid. So for the admixture, we can add something like dust or something, ash incinerator or something like that. You can add it and it becomes attached. So that's the old method. Pozzolans are similar to the cement. We can add lime, which hardens, if you remember. New clays that they've made up where they've modified regular clay, also modified lime like this. Companies have come up with these. Thermosetting organic polymers need thermo, which is heat, and they get hard. So companies will sell you that. And also thermoplastic material. So companies will patent these things, and if you look on the web, if you ever get a project like this, you'll see all different kinds. Let's go through each. Oh, the last one is vitrification, glass making. which, if I'm not mistaken, somebody at Savannah River may remember this. I thought they were vitrifying some of the radioactive waste a few years ago, making it long cylinders to try to hold in the radioactive component. Okay, cement. As I said, that's just basically Portland cement like you buy at the store for making sidewalks. You grind it to a fine powder, and that's what's already there. You rehydrate it with water that encapsulates the waste. That's how concrete is made. You know, it produces heat when it's setting. It's actually a chemical thing happening. And obviously cement has been around for 2,000 years because the Romans used it. So, as I said, it's old technology, but in this case we can use it. I think they tried to use this in Colorado for radioactive waste too. But they were going to like do the sidewalks in Golden, Colorado with this radioactive waste. But obviously I don't think they got rid of the radioactivity. It would hold the hazardous parts, but there's some problems there. There's a difference. The cement is this limestone and silicate, where the concrete is the cement with the aggregate. So all civil engineers know the difference between cement and concrete, right? So in our yard, our pool is actually concrete or our sidewalk. We have something new. It's called a pozzolan. It's actually a material that reacts with lime, which is similar to cement, of water to produce a cementatious, cement-like material. Fly ash is one. You probably heard of them using fly ash from incinerators for things, and they add it to cement. It's an additive, but actually you can use it by itself too. Furnace slag, what's left in a furnace, dust, they're all useful. So if you already have that waste somewhere, you might want to use it to bind up your hazardous waste.
Do you use like cigarette ashes?
I don't know, why don't you try that?
Okay.
I don't know, what's left from cigarette ash? It's just probably the tobacco leaf. It's probably organic. Not very good, I don't know. You could try it for your PhD. Once you give up smoking, no. So sometimes, you know, this used to be a waste. Nobody wanted it, but now if you can use it as an additive for something people want, it becomes a product. So that's been happening in the past 10 years or so. Oh, we have the lime. I don't know why that's up there. This works really well for inorganic sludges, but it changes the pH because it's basic. So you have to look at that too. If you had something that was very acidic, it would be good to add the higher pH. You took away the toxicity due to the low pH. We want to look at the whole kind of waste. We have the modified lime. Usually that one is used for organic waste. You're going to result it in something that can be used as a fill for building roads or something like that. So you don't have to send it to the hazardous waste dump. And also we can do the new organically modified clays, and they actually take away some of the cations and they replace them with organic cations. Again, this works good for organics, which is what clays do really well, but they're going to cost more because obviously the manufacturer's got to do something. Then we have the thermosetting. They use a catalyst to form a polymeric medium. It's macro encapsulation. Sometimes it can leave a liquid waste. We tried doing this for one of our projects a couple of years ago, and it didn't work really well. It might not have been a good product, but you'll see companies with products. Obviously, this is going to be very expensive. And the last one, the thermoplastic, too, are going to be more expensive. Using molten thermoplastic materials at a high temperature. Something like paraffin, you know, like wax, is something that's thermoplastic. So when it's warm, it's molten, but when it cools off, it's hard. So that's an example. Now, is that going to work for hazardous waste? I don't know. Because as soon as temperature gets up, it's going to melt down. So it would have to be a special kind of paraffin. But I think there was one more. Oh, the glass making. The vitrification, like I said, is getting a lot of talk nowadays. Because to make glass, you just need silicate, sand. Okay, most soil has got silicate in it. So your natural soil can be turned into glass. But you do need a high temperature, like 1600 degrees C. You can do it in place, in situ, in place. You just pass a big current. And we had this happen. We came up with this really good alternative to treat hazardous waste, and we went to the contest. A different school did in situ vitrification. Of course, they won. They actually had a great big generator, and they were putting pulses, oh God, high voltage pulses into their soil, and they made vitrification right there at the contest, so they won. But it's not that difficult to do as long as you can get the temperature up, which if you had a lot of voltage. Whoa. Uh-oh. Am I on? Okay. Fall out. What did I do wrong here? Anyway, if you know what obsidian rock is, you know that black glass-like rock, when it breaks in kind of a roundish pattern, fracture pattern. Seen obsidian? Yeah. Anyway, that's what it looks like. I mean, that's what obsidian, it comes from volcanoes. Same kind of thing. It's not really good glass you can see through, but it is a glass structure. Sometimes if you're doing it in situ, you're going to have gases come up that you don't want, so you will have to capture it. It's not just something you can do out in the open. But look at the rates. That's pretty good. 3 to 6 tons per hour, they say you can do in situ, in the ground, without even digging anything up. Now, obviously, you're going to have to do some research on that, because how deep can you go? You're going to put a pulse through it, a high voltage pulse.
It just makes it like
Glass, hard,
underneath
hard,
the ground.
right, yeah. And
What happens, then you have to keep people away from that area, you don't build on it?
I wouldn't build on it, but if it's, when you do the test, we'll talk about tests, if it can't be pushed out or leached out, then it's fine. You can do anything, but I wouldn't put a house on it. Who knows? I mean, I wouldn't want my house on it. Yeah, you can do any kind. Recreational facilities are good on old sites, reclaimed sites, because they don't build any heavy structures. Like I said, they were looking at it, the Department of Energy was looking at it. You can also do it, this is in situ or outside, you can do it in plant too. A couple EPA sites have done it. So, you know, it's not as new as it used to be. It's been tried in all different applications. So there is a lot of data on vitrification. Testing. Now this is the important part, what you brought up. After we do whatever we do, concrete or the clay or whatever, we have to make sure that there's going to be no leachate. Okay, the two words, we talked about leaching. This is leachant, the fluid to which the contaminant is going to be going through. Well, you know, we want to look at real-world conditions. Outside, we have the rainfall, right? It rains. So it would be good to look at the normal pH values of rain. Say it's, you know, 6. So that would be a good leachant, the water at 6. And some of the tests, though, use acid just to make it even harder to pass, or, you know, more rigorous. So some of them use kind of high pH acids, I would say. So you want to look at the environment, which you're going to be into. Then we have the leachate. That's after it goes through our solidified mass. It would pick up the chemicals. That would be the leachant. Leachability is the overall ability of stabilized material to leach contaminants. So the higher leachability, the worse it is from our standpoint, because the leachant will come out as a leachate, and it can get in our groundwater and contaminate the groundwater. So like at the Arsenal, that place we talked about that used the solidification, now it rains, and they didn't put any liner under it. If they didn't put a cover on it, we're going to get leachate through it and into the groundwater. So, you know, you've got to be very careful that it really worked, that we're not going to get that. Okay, there's lots of tests, but the two main types, regulatory, which is basis for decision making. Like, you know, RECRA may say to use the one test, but some other law might say to use a different test. So you want to use it for whatever the decision making is. There's also predictive tests. Like in the lab, so we've got a new method, or we want to vitrify some other chemical, we would do the predictive test just to see if it does leach. We may try different tests on it to see if it leaches. Okay, and then there's the investigatory, study of basic mechanisms, where we're just looking at, say, an acid ability to leach something. So that would also be in the laboratory. So the ones that EPA is worried about are more the regulatory testing. Okay. Like I said, there's a whole bunch of methods out there. Things that make them different are the leachant to waste ratio. They may say a few milliliters of the water or acid, and then, you know, a certain size, particle size, or weight of the waste. Also, surface area of the waste. Do we use a hunk of the material? Usually we have to grind it up and sieve it to a certain size. And like those sieves we use for soils lab. So say size 20 sieve. And that's the size we use, which is the surface area, so it's the same for any waste. The leachant, as I said, it could be water, it could be acid, something else. The pH of the leachant, again, goes back to what it is. Contact time. Is the test run 24 hours, 48 hours, 11 days? So all the tests are different. Obviously, you're going to do the test that's required. Another thing is, does it have to agitate? Are we going to be mixing it or somehow making it agitate? Number of leachant replacements. Oh, is it better to just dump one amount of leachant over and then agitate it? Or do we put the leachant in, take it out, put more leachant in? What would be more normal? I mean, in a real-life situation, we're probably putting clean rainwater in every time. So the different tests have different ways of doing that. And then extraction vessel. What's it in? What do we put it in? A glass vessel. So they're all different. Temperature, obviously. Could be different in summer and in fall. Okay, the one that we mentioned before, the EPA one, is the paint filter test. We use the free liquid in bulk and containerized hazardous waste. That's used by EPA for the RECRA, the Hazardous and Solid Waste Amendments. That's the one they use for that one. Then there's another one, liquids release test, which is what it sounds like. Stress is applied to the solid, and we see if it's going to come out. So it's like the spongy thing. We have the extraction procedure toxicity test. We sieve the material to a certain size, and the leachate goes through it and is tested. and that's not a very long test. There's a toxicity characteristic leaching. Now this one's real common. TCLT test, you probably heard that. TCLT? It's one of the common tests. That's a regulatory, another spelling, regulatory test. It's real common. There's an American Nuclear Society leach test. There's a uniform leach test. There's all kinds of leach tests. I would say the common are these two. And TCLT is real common for like metals. So we're going to bind it up in some kind of concrete and make sure the metals don't come out of it. Oh, there must be another one there that I'm not getting. Anyway, there's a whole bunch of tests in the book. So for the specifics, look at the book, or else STM standards would have more on it. Okay, there's also other tests. If we're going to use it for building, let's say we're going to use it as roadbed material, we're going to make sure it works. Moisture content is one thing, wet and dry bulk unit weight, specific gravity of the material, particle size distribution. This all sounds like soil stuff, because if we're going to use the soil, the same thing. We might have to compact it. Same thing if we're going to use it on a roadbed or whatever we're going to use it. See if you can penetrate it. We look at microstructurally what's happening. So we run tests, strength tests, consolidation, tensile and torsion, consolidation, conductivity. Is the water going to go through it, or does the water stay on top? And durability. Sometimes they actually use this stuff for the roadbed itself. You mix it in concrete, right, the fly ash, and we use it as a road material. So this would all be really important as road. How long is it going to wear? And so we have the chemical test, the leachability test, and the physical treatment. Okay, where do we use it in the field? First of all, we can do it in drum. So we have our big 55-gallon things. We can stabilize the drum. We add the reagents, mix up, and store it. It's a little bit nicer because, barrels eventually leak. They're not going to last 25 years. And even if you send it to AMEL, the hazardous waste site here, you're still liable for it. So some places will actually do this solidification before it goes to AMEL. That's kind of a good idea. Okay, because the liability factor. You can also do things in ground, in situ. We can mix it in the ground. Say we have a clay, well, not a clay, a sandy soil, let's say. We can vitrify it because sand is silicate method, but it costs a lot. Or we can use augers. Drill holes, mix in the concrete in situ, and then make it solid. So you don't actually have to pull it all out. So there's some economy here on some of these methods. You can also then take it out, ex situ, take it out to a plant, mix it up, the normal method, and then add grout or cement or pozzolans and get it that way, and then put it back in the barrels or whatever you want to do with it. So there's different ways it's used. As I said, vitrification is nice. Vitrification, though, is very expensive. Okay, design. A lot of things, and this all makes sense. The curing time is important. The vitrification happens like really quick, no problem. But with the concrete, remember concrete takes 90 days to reach, what is it, 90%? No, 30 days to reach 90%. Is that right? Something like that. Civil should know this one. Right? We look at the 30-day strength. Is it 90%? Anyway, it takes a long time. It takes a long time for concrete. It's not like something we're going to do overnight. Also, some things can increase or decrease. Like concrete, while it's curing, you've got to keep adding water to it because it's producing heat and using up water, so we have to look at that. Cost, as I said, vitrification is nice, costs a lot. Schedule, how long is it going to take you, how many tons per hour can you do. Type of mixing required, that's going to add cost. If we're going to leave it in or take it out of the soil. With the concrete, the heat generation may be an issue. If anything is flammable or off gas or whatever, heat could be a problem. So you have to look at overall all these things, and also gas generation, mixing time. Well, anyway. Okay, there's some case studies in the book. Some of you may look at this when you do your site assessment, your SITE thing. You may see some of these. So there's a couple examples in the book. But like I said, DOE's has been doing this. Even here at the Arsenal, we've been doing this. The Army Corps does this. So it's been around a while. It is a known thing. Okay, I think we're done. Okay. Like I said, that chapter wasn't much because it's kind of intuitive, mix it up, harden it, but we don't want it to come out. So the question is it going to stop the migration, which then stops the toxicity to humans? So that chapter's not so bad. Let's open a different chapter. Let's do chapter 12. Okay. Okay, now chapter 12 is a little bit more involved, and it said you're not going to be doing the homework, so okay, thermal methods. We talked about physical, chemical treatment already. The stabilization really isn't a treatment. It's kind of just stopping it from migrating. But thermal methods are good treatment. And they're either very high temperature or lower temperature. And again, it makes a difference in cost and whatever your waste is. Now, a lot of organic things can be burned, because at home you're burning wood, which is organic. You're burning your cigarettes, which are organic. Okay? So that we know that they burn. And we can use it for our own methods to get rid of waste. Okay? The biggest one, obviously, is incineration. But there are other things where they use low temperature, high temperature to get off volatiles. I don't know if have you heard of where they take the soil, desorption it's called, low temperature, high temperature desorption. They take the soil out of the ground, you heat it up, and then your volatiles will come off. So we have TCE contaminated soil. We can take it off, the volatiles come off, we get them, let's say, in activated carbon. When we clean the soil and we put it back. So for thermal methods, it doesn't have to be incineration. There are other things out there for off-gassing, but this chapter is mostly concerned with incineration. And we're talking here hazardous waste, not just the kind we have in Huntsville, which is for our municipal solid waste. So it's the same idea, though, but I'd say a little bit better quality. So we use them mostly to destroy organic components of waste through high-temperature combustion processes. Why don't we use it for inorganics?
So they wouldn't have it in the smoke, right?
It either goes up in the smoke, right, or it stays in the ash. Remember we talked, whoever went to the incinerator last year? They have a lot of metals left in that ash. So it usually stays. And if it goes up the stack, it's even worse. So that's why. Organic waste. You always have the ash. We had fly ash or we have bottom ash. Fly ash is the lightweight that comes up. It's got to be caught. The bottom ash is the heavy stuff, which could be like the metals down at the bottom. So those then will also have to go to landfill. So it's another thing that has to be looked at. I don't know what that was. Okay. The regulation, again, is RCRA, because we're talking about hazardous waste. And it's the hazardous and solid waste amendments, which were the tough ones in 1984. So that's the major thing. The section is, it's 3005 section with removal efficiencies. It must pass the liquids release test. Okay. And we look at DRE, destruction and removal efficiency, which is, wait, one more. Whoa. Don't want to do that. The weight in or mass in minus the weight out divided by waste in times 100%. So if you remember, if they say it's 99.99% efficient, that's actually DRE. Now a lot of these we want to go to 7 nines. 99.99999% efficiency, because we're talking about hazardous waste. They've even gone to 9 nines. Okay, because you're talking about putting in, say, a couple tons per day of, say, nerve gas. A couple tons per day. So even a couple pounds per day of output is bad. So we're talking about high efficiency on these. Okay? So remember, this is not like here in Huntsville. And this is what they're building out there at Anniston for the nerve gas. Something like this.
There's one in
Right. There's one on that island somewhere. There's one in, anyway, the Army Corps guy, he could probably answer. There's lots of them going up. A lot of our management office does it here at Army Corps. Okay, what is combustion? Does everybody know what combustion is? Especially Lynn. She's got a lighter. I don't even have, the other day at home I couldn't even find matches. Whenever I'm talking to her on the phone, she's like, I said, what's wrong with your breathing? She did quit once. Okay, what you need, obviously you need oxygen, right? In your fireplace at home, you can't shut those doors and allow no oxygen because it would die. You need oxygen, and we give it excess oxygen to make sure it works. You need a fuel. The wood, the cigarette, in our case is a hazardous waste. An organic hazardous waste is a fuel. Because what do we use at home to burn? Propane? Somebody have a propane gas? Gas? On your charcoal? Lighter fluid. Okay, they're organics, right? So the hydrocarbons, but other things are fuels too. Waste containing sulfur, halogens, nitrogen, and organics. Some of the industrial waste or hazardous waste can have inorganics. So sometimes we will burn things that will have metals in them, but the whole reason we're doing it is because of the organics in the waste. And the nice part is if we can get 9 nines efficiency, that means we have 0.00001% left. So it's really good reduction. Okay, if it runs right. And as I said, the metals may be problematic in some of these. Okay, how do you do a calculation? We have to know what's in it. The same as in intro class when we looked at butane. Okay, and you looked at how much oxygen, the oxygen demand of using butane. You have to know the chemistry, which easy for propane, butane, all those kind of things because we know, but a lot of these wastes are bad. There's a table in the book. Oh, temperature. Find the temperature, latent heat of vaporization, a couple different things to solve these problems. Let me do an example. Okay, excess oxygen is one of the main things because usually we can't get mixing really well. With all our engineering advancements, you think we'd have mixing down to an art, but we don't. To put a mix the air, usually we're using air, not pure oxygen, into this. You know, we could add exactly the oxygen demand if we could have complete mixing. We don't usually have complete mixing, so if we don't have excess oxygen, we don't completely combust the organic, and we're going to get something out the stack we don't want. So really the most important thing is mixing and the oxygen. So look at one of the problems from homework, 12.1. Can we go to the overhead, Jared? I hope we can read this. Maybe you can't. It looks bad here. Okay, at the end of the chapter. Oh. It's not showing up very well. Okay. And it says, 1,500 pounds per hour for waste containing 40% benzene, 50% toluene, and 10% water. Now, obviously, we know what those chemicals are. You can look those up. Is burned with 25% excess air. Oh, I wonder if I can zoom down. Wait a minute. I don't know. It's just showing the back. I don't even have a piece of paper. Yeah, well. Oh, there we go. Is that better? Okay. Okay, for these problems, it says determine the total heat release and the percent of volume of each component in the flue gas. Okay, so we want to know in the flue gas what's coming out. Okay, so we know here what we've got: benzene, toluene, water. Okay, write those down. We look at the heating value of these things. Obviously, toluene, these sound like they're really big organic chemicals, right? Like propane kind of stuff. So they do have a big heating value. 18,210, 18,440, that's BTUs per pound.
Make it a little bigger.
Let's see. Okay, BTUs per pound. You see that? And we have molecular weight, which get off the table. Okay, they're high heating values. Like, remember we went to the incinerator here, he was talking about rubber. Rubber is extremely high too. Okay, so then we look at the total thing. So here we've got the three contaminants here, percent by weight, which we're assuming that it is. Okay, and then the pounds per hour. Okay, he told us 1,500 pounds per hour was given. So of that 1,500 pounds, right, 40%, so 600 pounds an hour. So now that we have BTUs per pound, and we have the number of pounds in, it's pretty simple because we can get the heat released per hour. Well, that's not hard.
Oh, wow.
Is this going too fast?
Oh, pounds per hour, you can figure that out. If you have 1,500 pounds and 40% of it is this one, you have 600 pounds. Okay, multiply by that. And this is released per hour. Now, huge numbers, okay? 24 million BTUs per hour. That's enough to heat the whole city almost.
24 million BTUs.
BTUs per hour, which is another engineering problem. We've got to get rid of the BTUs, but they didn't ask for that here, did they? Okay, but now we got to get into chemistry. This is the easy part. Okay, that was the easy.
Go back now to the last column of that table that you're showing.
It's just multiplied. 24,756,000 BTUs per hour, just from that waste. Now remember thermodynamics? Where's that stuff going? Okay, that's the easy part. Now we got to look at the chemistry. We don't really need the numbers.
Just go 600 times that.
Yeah, just that times that. Okay. What the problem here is, okay, what was the problem? We've got 25% excess air. That's the problem. Okay, which means we have to figure out the oxygen demand, and then we add 25% extra, and then we'll figure out what's left. That's the hard part of the problem. Okay. So the first contaminant here is benzene, C6H6. Okay. So we had 600 pounds per hour. We have the molecular weight of 78. So we have 7.68 moles per hour going in. Right, we're going to convert everything to moles. Right? Because if you do the reaction, right, you got to have moles, moles, moles. Right? We're going to do a little thing. So we've got 7.68 moles. Whoa, that's not important. You can do that. Okay. So then we've got the other two contaminants. Okay, we're just converting them all to moles per hour. Which we know, you did this in intro class. Come on. This is intro stuff. This is not the hard part. Okay. Now we just have to make the equation, which is what? We're just adding oxygen, right? Each of those separately, though. Right? And balance. And then we get the amount of oxygen we need. Okay, he remembers that. Somebody remembers that? Okay. So here's the first equation. That's benzene, right? We said we have 7.68 moles. Okay, we have 53 moles of oxygen once we do this. Okay. What do we produce if it's fully combusted? And water. We're assuming we're going to add enough oxygen. Okay, so we have no other byproducts. So that's why we get CO2 plus water. Pull that out a little bit. Pull that out. Okay, we're still not at the hard part, guys.
You're going too fast. You can't even follow it.
Nobody else is writing it down. Everybody else knows this stuff. Okay, so all we're doing is doing stoichiometry. Okay. Now the pounds should make sense now. We started with 600 pounds. We can do a ratio that's not even on here because you know how to do ratios. The moles to the pounds, right? So anyway, both sides have to equal out. Do they? They should. 2,300, 2,400. Yeah. Okay. So both sides in pounds have to equal out. Moles have to equal out, which is stoichiometry.
How many H2Os is that for benzene?
3. Yeah, you have to because you have 6 over on the other side. Anyway, but these equations you keep using over. Okay. So we have the air to burn. Well, we know that air isn't totally oxygen. That's the only reason we're using that. It's 21% oxygen, right? So every 100 grams or 100 pounds, 21 is going to be oxygen. So that's where you get this 100 divided by 21 because it's 21%. So if we have, actually, where did they get 57.6? This should be 53.8. This isn't even right. But, okay, that's just the conversion factor to get air. Obviously, we need more air than oxygen. So that's how we get that. But we wanted 25% extra for excess air. So the 1.25 is just like the factor of safety. 100%, no, we're going to use 125% air.
And that should be what, 53.8?
Yeah, that should be 53.8. It's in moles. Yeah, that's 1.25, but that should be 53.8. I don't know where that came from. It's in moles per hour. Okay, whatever that's going to be. And then, okay, so we got moles per hour here, right? That's in moles per hour. We can convert that to pounds per hour because that's what we want to know, how many pounds of air. You tell that to a supplier, moles, they're going to look at you. So you want to know how many pounds of air. So we just know the molecular weight of water and we multiply that. Okay, so that's how many pounds of hour. That's just for one contaminant. Right? We've got to do the same. But what else do we know about air? Here's where the problem is, chemically. What's the major component of air? Nitrogen. So we're going to have nitrous compounds in the flue gas. Air is 78%, 79% of nitrogen. So also, out of that here, air, how much air we're burning? 342 or whatever that is. 79% of it is nitrogen. So we have to also account for the nitrogen since it's the major component. And we're not going to be burning that. So you see this little thing with nitrogen. We're going to have 7,585 pounds of nitrogen out in our flue gas, which is not little. That's just for the benzene. Everybody see that? So if we're looking at percentage of things that are coming out, we also always have to look at nitrogen compounds. Okay. All right. For toluene, let's do the same thing. Toluene plus oxygen, we balance it, let's get the 9s and the 7s and the 4s, balance it, we got the moles, and then we get the pounds. Same thing, we get the moles per hour, we get all that. Again, nitrogen. What else? What about the water? Was there water in here? Was there water? There was water, right?
I don't know. We can't do
What happens to water? It was in the original question. What happens to water? Does water burn? Right, water doesn't burn. Water's not burning, so it's not a fuel. Okay. So what we've got here is, the question was, flue gas analysis. What's going up the flue? So do we know that? Sure, we just did those equations. Those two equations we did for the toluene there and the benzene. Okay, we've got numbers, right? Pounds per hour and things like that. Okay, so we've got both. It's a question. I mean, the answers. We've got moles per hour for CO2. Okay. Oh, this isn't even right. The equations are wrong. Don't look at the second one. It's not even right. Look at this equation. What do you see problem here?
O2 is not.
Yeah. It's CO2. CO2. There's a problem there. Okay. Hopefully these answers are right. You produce CO2 in water. Okay. Okay. So what we've got the CO2 from both reactions. We've got the reactant H2O, which went in. We've got the fuel H2O, which is what's coming out. We've got the O2 that we put in, that we need to put in, the excess O2. Okay. And we've got nitrogen. Now, obviously, nitrogen is huge. Look at nitrogen, 615. It's 2/3 of the moles. And we looked here, too, in the pounds per hour. We can convert to pounds per hour. It's also the huge component, obviously, if we switch from moles to pounds. But the question was, what's the percent by volume of all this? So all you need to do is take the total volume here. Well, I don't have it, okay, and figure out here what each one is. So it's got a total 100%, this last column, which was the answer. And again, the biggest one is the nitrogen, which wasn't in the original hydrocarbon, right? But since we used air, we're going to have nitrogen. So you can see our problem with using air. Now, obviously, nitrogen, well, these numbers aren't right. I wouldn't copy down the numbers, just the process.
Well, what's the,
Well, moles per hour, you just add up your moles. Add up your moles from your two equations. You only have two equations. You have benzene and toluene.
What's that say, flue gas?
Flue gas, that was what they asked for. What's coming out of the flue? Okay, that's what's left over, right, or the products after. We're assuming complete combustion. You notice we don't have toluene or benzene in there. So we're assuming we're getting complete combustion, which, isn't truly true, but it could be 0.0001 something, 10 to the minus 9, but small anyway. Okay, so that the neighbors, when they find out there is no benzene, propane, whatever coming out of there, but we do have this. So they will have a permit from the state, right, to pollute, which if you ask, they're supposed to tell you what they're putting out. So there isn't nothing that's totally, completely clean. Something's coming out. But in our case, CO2, some water, which is steam, like we see at our incinerator. We see that steam all the time, which worries people. And also we have some extra O2 if it didn't all mix, and nitrogen, though. Okay? Now, sometimes you get carbon monoxide, which isn't on there. So if it doesn't go completely to CO2, you get carbon monoxide. So you can see how it's done. Now, that's a simple one. Now, most hazardous waste is a lot worse. Let's say the gas they're using down at Anniston. That stuff is horrible. They probably don't even know all the products. And we're making assumptions that it's totally complete combustion, which means we have an excellent mixing method. So we're adding the excess air of 25%, and we're assuming it's coming up the stack because the rest of it's used. So, again, it's just stoichiometry, and it makes sense if you know the products, if you know the reactants. Complete combustion, we get CO2 and water in these cases, and then we just convert from moles to pounds, but we can't forget the nitrogen in air. Now, if we were using oxygen, we wouldn't have this problem. But can you imagine how many tons of oxygen we'd have to put in here? It would just be horrible. So they use air because of that. So air is the common one, but just remember air is only 21% oxygen. Okay, so obviously, get back to this. Oh. Hey, Jared. Okay, back here. Excess oxygen. Obviously, it's going to be high temperature. We're going to burn at high temperature, plus we're producing all the BTUs. Extra fuel, some things aren't as nice as this example. Some things don't burn by themselves. Maybe they have too much water in it. Like I say, it's sludgy stuff. You might have to add or mix things together. Type of combustor, we'll talk about this. There are different ones out there. Something that uses a catalyst. There's liquid, injecting a liquid, or fluidized bed reactors. So they're all different kinds out there. Now if we have a gas or vapor, a lot of gases are combustible. There's a table in the book that tells you how combustible. The problem we have to look at is explosive limits. If it gets too high, too much pressure, things will explode. We obviously don't want that to happen. Our incinerator goes away. Okay, everybody, I think it's seen a flare. It's waste gas that are above the limit, and they flare it off. When we went to the wastewater treatment plant at South Parkway, they were flaring off their methane, burning it. In Saudi Arabia, I see that in Kuwait, they flare off their natural gas. They don't collect it, they just flare it off. And that's how they get rid of it. They do it on purpose.
They don't use it for...
It's just so cheap out there, they don't need it, yeah. But now here, we would collect it. So there's sometimes you do it on purpose, the flaring, but you don't want it to flare by itself. A drawback. Something, vinyl chloride, which is a degradation product of a lot of different things, is bad. You need some additional treatment on that. It won't work. Also, aqueous waste. Anything that's real sludgy with a lot of water, obviously we're going to have problems with it. It may need extra fuel or mixed with something. Whatever's left, you know, I said we have the two ashes. We have the fly ash, we have to collect it, and we have the bottom ash. We're going to have some kind of ash landfill or some way to recover that to get rid of it. Okay. For the airstream, the flue gas, we need scrubbers. Obviously, even if we have this low level of the contaminant, we're probably going to have to clean it. So there are different scrubbers available, which I think this chapter goes into. And one thing that's obviously needed, since this is hazardous waste, they have online, real-time monitoring. Make sure that the scrubbers or whatever they're using is working. So, but even when we went to the municipal incinerator, they had real-time. If you look at the screen, there's somebody watching all the time. Plus, then they had some kind of emergency thing that when the bell goes off, the whole treatment, it shuts down. So even in the regular land, on the incinerator, it works. But these are even better. There can be a discharge from the liquid. If we're injecting liquid like a jet, kind of a jet liquid injector, we can get wastewater discharge, so you have to be careful. Okay, volatile organic compound incinerators. Usually it's catalytic VOC incineration. The airstream is first preheated usually. We want to get it warm. So we use the old BTUs that we made before, so we have that heat. We can preheat it, which works better. And then the VOC is burned. Eventually the catalyst on any of these, the catalyst doesn't work forever. So it gets coated and doesn't work anymore. So again, the monitoring helps. There's also called thermal VOC incineration, which uses no catalyst, which then you don't have the catalyst poisoning, so you don't have to monitor the catalyst. But I said you can do liquid injection, kind of a stream. You just push it in. It's common. There's an atomizer injection, which makes it into small droplets and puts it in the burner. The small droplet then has a bigger surface area, which it helps within the oxygen. So the mixing is better for the oxygen part. We also have, we can mix in air. We also have usually two combustion units, the first one and the second one. So secondary would probably be hotter than the first one. Sometimes units use excess fuel. They may have a propane tank or something to get it started. So if there's too much liquid, they'll need that. They need, for a starter, something like 4,500 BTUs per pound, so something extremely hot. And as I said, excess air is really important. Depends how well you mix on how much excess air, but it can be up to 60%. Design factors. Obviously, you're going to do a trial burn. You have to get at least 9.99, but nowadays they're getting 7 or 9.9. So compliance is very high, so you've got to try it. You try the atomizers for aqueous waste. You can also, though, buy mobile units. If it's only, one site, and it maybe only be a couple months to clean it up, rather than building a permanent incinerator there, which is probably you need if you're working there a couple of years, but you can get mobile units you just bring on site, and they're in a big kind of house trailer thing, and those work really well. So that's a cheaper alternative, so you don't have to build the real building. Most times cheaper for smaller jobs. Okay, incineration. When's it good? It's a good option for a hazardous waste site. If the cost is good, like I said, if you have to build a complete incinerator from scratch, it could cost a lot of money. So unless it's a big site, it might not be useful. If you can get a mobile incinerator, save you some money. And you want to check everything before you do it, obviously. The trial burn thing, make sure that if you know the equations, how they work out, sometimes that's not all known. So you want to check into all those properties, especially thermodynamic of the waste. Because if you build it and it doesn't work, then there's a big trouble. So you can make sure that it works before you build it. Also, we know that VOCs are a good fuel source, but sometimes you can mix waste together. You have something that's volatile, acetone, and something else, hazardous waste, that may be not so high in BTUs. That might be a good thing to mix together. Also completely destroys BTX, which are groundwater contaminators. Also pesticides work extremely well. Now, as I said, vinyl chloride isn't treated that well. So if there's vinyl chloride in it, you're going to probably have to do post-treatment or pre-treatment for the vinyl chloride, which is extremely toxic. So know what your waste is. Okay. For solid waste, there's different kinds of incinerators. We're talking about the liquid, injecting the little tiny pieces. Usually with the solid waste, we have a grate incinerator, and that's just what we saw when we went here to the incinerator. Stationary metal type grate, you know, you have a grate at home in your fireplace, kind of like that. The one we saw is kind of up like this. But based on your size and the amount you've got for your grate size, you can get a hearth type or you can kind of rotary. Now, the advantage of turning around is you can get the air mixing that way if you have a rotary type hearth. Usually they control the air, or they have a 2-chamber fixed hearth. So there's different designs which are in the book. There can be more than one hearth on it. We have 1, 2, 3, 4, which will heat it up then slower, or one hearth. So again, different companies do different things. You may contract with a company, and that's the kind they do, and they've had experience with it, and it works. So that's what they always do. So you want to check into different companies and how well they work. And that was it for that. Okay. A little bit more high-tech is called fluidized bed incinerator. Instead of the fixed hearth arrangement, we've got sand or something on the bottom, alumina, and then you have the pressure from beneath. What that does is push up the sand, and that's what they call it fluidized. It's kind of like up above the floor. So we get a good mixing of air. So it's not just sitting down there flat on the bottom. And that's what fluidized, it sounds fancier, but that's all it is. It's air there. So you get good mixing just from the airflow up from the bottom. So they all have advantages, disadvantages. Okay. Whoop. Okay. You can do oxidation, which is really what burning is. It's complete oxidation. Or there's something called pyrolysis. We talked about this a little bit because we talked about activated carbon. That's made in pyrolysis. If we oxidize completely the organic material, it would go on to ash. But if we heat it up and limited air supply, it turns into activated carbon. It doesn't go all the way. A similar example would be charcoal at your house. Charcoal for cooking, right? They take wood and they just burn it. But they don't burn it all the way down to ash. You do that. So it's just part way oxidized. Okay, and you can think of pyrolysis similar to that. It's only partially oxidized. So you just use starved air. In some cases, you can do that and get rid of a hazardous waste. As I said, in incinerators, sometimes they have primary chamber and secondary chamber. A lot of times the secondary chamber is to meet the regulatory requirements for the 99.99% and has extremely high temperatures. And you have to leave the gas in there at least for 2 seconds, which doesn't seem like much, but you know, if you're pushing through a lot of material, that you can make sure it stays in there that long. And the secondary chamber, sometimes they're horizontal and sometimes they're vertical, so there are different designs out there. And you know, the companies have their different reasons for doing it that way, and I'm not sure which mix is better. Obviously it has to have refractory lined, which means it doesn't melt. Something that doesn't melt at 1200 degrees. Okay, they have to have a thermal relief valve. If it gets way too hot in there, say we miscalculated and we didn't add a factor of safety, we could have an explosion. So there's usually some automated valve that will let off the pressure. Also, what if we had a power failure? Okay, so all of our devices, our control devices wouldn't work. Okay, if the water flow, let's say we had a water cooling system, the water flow, something happened. It's happened at nuclear power plants already, where the water flow stopped. We've got to heat up. So in order to stop a catastrophic failure, we have some kind of relief, which should be automatic and not electrical, because that would be a problem if it was electrical. Usually it's the top of the secondary chamber. We don't want that to happen, but it's just kind of a safety feature in case something happens. Obviously, the important parts are your temperature and your air and all that. But in the design, you also look at how you're putting the material in. With the liquid, we can have the liquid feeder, the injection. With the solids, we're going to have to worry about some kind of a system, belt system to bring it in, because obviously people aren't going to be shoveling it in. It's hazardous waste. So it's going to have something self-enclosed and totally operational by itself. First of all, we want to store the waste. Usually they use standard size storage, vertical vessels on legs, 20,000 gallon capacity. You have to have leak detection, because we're talking about hazardous waste. We have to know how big the volume is. it has to be equal to the largest tank. So we're going to have excess. We're going to have extra tanks all the time in case something happens. You know, if something happens to the incinerator, we're going to have to be able to store this stuff on site for a while. Okay. Again, we got storage. For bigger solid waste, we use drums, boxes, roll-off boxes. Depends on what the stuff's stored in. Usually we have to cover it. And even when we cover it, what if one of these barrels leaks? We're going to have containment, probably concrete barriers around to contain. So obviously we want to have secondary, probably even third, tertiary type containment so this stuff doesn't get out. We have to look at the feed system. We want direct feed. We want to make it as efficient as possible, that it could take a drum, a box, a roll-off, whatever. It could take all different kinds of things. So you don't want to make it specific unless it's like the Army and they have specific tanks that they're doing for 2 years. They'll be more specific than a regular hazardous waste thing that just takes any kind of waste. If you're going to batch feed, which is, just dump one at a time, you're going to have problems because we usually need to have that BTU and fuel into there all the time, continuous. So we'll see most of these will be continuous feed. Okay, flue gas. How do we get rid of all that extra heat? Boilers, water is really good, right? Water's free. You'll see some of these placed on streams or rivers because free water. So you bring the water in, you can raise the temperature a little bit. So you can use the boilers too if we can recover the steam and use it for heat generation. Obviously, they don't do that here, but you can make steam and sell it. So the steam also can make electricity. So you can recover energy. You need to quench that flue gas. It shouldn't be coming out at 1,000 degrees C out the top, right? So somehow you're going to have to quench it. You can quench it with air and water. Just spray in, air. Okay, we're talking about gas there, so it shouldn't be too dirty. You got to figure out how to mix it and how to inject the air. So there are all different ways out there. Okay, air pollution control. We've got a couple different things to look at. We've got particulate or little matter, particle matters. We've got dry methods and wet methods. We can impact or hit something. We can do centrifugal. We can turn it around and make it come apart. We can filter it out with air filter type things. We can use electrostatic just by the charge of it. So we use electrostatic plates. That's very good. Either one of these. But when you look at these, you're going to have to look at what you're going to do with that afterwards. A wet scrubber. We're going to use a lime wet scrubber. What are we going to do with that waste? What's in it? What can we do with it? This was hazardous material. Is this going to be hazardous material? So that's an important issue there. Look at all the byproducts. Okay, we might have acid gas. For acid gas, we can do dry lime injection. Okay, not wet scrubber, but dry scrubbers. More often you see these wet systems. We can do adsorption. We can do wetting, added chemical. We can use wet lime scrubbers. So just depends on if it's a gas or if it's a particle. What are we going to use? Okay, what else about design? We've got fans and blowers. We've got coolers and condensers. We've got mist eliminators, stacks of the gases. So a lot of different parts to be designed. Obviously, not one person's going to design this. But there are companies that specialize in this. But as you say you're a project engineer, which is probably possible with most of you here, you may be saying, we're going to use this company, why? So you really want to look into everything that they're doing, not just part of it, and make sure that they've done these applications before. Okay, obviously we need instrumentation, extremely important. If we've got this stuff flowing through all the time, do we have temperature flow, pressure, pH level, automatic speed cutoff? We've got the air, what's going on in the flue gas, everything going on at one time. Well, now that we have all these satellite links, SCADA, a lot of times they'll have the computer there and then they will be uplinking it to the major office of the company. And so somebody will be watching all the time, even if there's not a person on site, which maybe there should be. But even if they're not there, there will be remote people checking. And then there's the emergency systems that will cut off everything. If there's an outage of something, everything will cut off. So, it doesn't have to be manned. But with the newer computers, it's not too difficult to do all this. So as I said, we're going to do continuous monitoring of all those things that might be coming out. We'll make sure that the unit is working. If it's not, we're just pouring out hazardous waste in the air, which wouldn't be good. Obviously, before we build this, multi-million-dollar structure, we're going to make sure it works. That's called a trial burn, and they are prescribed by the CFR, so they do have to be done beforehand. Okay, and obviously, we do have to monitor the flue gas. That's about it. So, as I said, the mobile systems are nice for small sites. Say we have soil, maybe only have an acre of soil. It would be a nice thing to do with soil incineration. Also used for non-recreational waste. But there's other things that are out there that, like I said, you can do low temperature devolatilizers. Low temperature may only be a couple hundred degrees. It'll take off the VOCs and the things that come off easily off of soil. So you don't always have to incinerate. It's still, there's other thermal methods out there. And I think that was it for that chapter.
Can we take a break?
Yeah, let's take a little break, and then the next one's really short. 13. Okay. Quick break? I know, the next one's real short.
I just have to go back.
Oh, okay. Well, I'm in the bathroom. She's in the bathroom. It's here. Little break. What's going on? Hello?
He's back.
It's on. It's on. Hey. Oh, we're back? No.
We're on.
Oh, we are on. Okay. All right, we're just going to do chapter 13. We're going to finish this lecture out with 13, which isn't very big. It's about land disposal. A lot of people have had landfilling already in different classes, but why do we use landfilling for hazardous waste? An idea?
Put it somewhere?
Put it somewhere. You don't want it to go to the air? It's got to go somewhere. Okay. Well, a landfill should contain. It should be similar to this fixation thing, right? If we can contain it. If it doesn't go anywhere, then it's not really a risk. So it's the same idea. Why do we landfill? Well, we have residuals left over. Let's say the ash from the incineration. You know, we've done all that we can do, and now we've got that left. Okay? If you have a plan, let's say, you know, we're making up a landfill, and we have a plan and a permit and all this, we can look at the safety. We can build it in. So there are still communities that do plan on landfilling the municipal waste, but siting hazardous waste is extremely difficult because people don't want it. You don't want the trucks rumbling through your area because they might dump something. You don't want to have, you know, the safety of your groundwater compromised and things like that. But if you're doing it, you know, it should be done well. So, and obviously we've got one here in Alabama over by
We have a
Tuscaloosa.
hazardous waste land.
Over in a mill, which is near Tuscaloosa, towards Mississippi side of Alabama, we do have one. Okay, when you're operating it, you know, it's got to be done really well, much more tight, obviously, than a regular municipal landfill. So one of the things that's required by RECRA is tracking of the waste. Remember, we have that manifest that goes with it from the generation site, from wherever it came from, to the trucker, to the disposal facility. So that then they should have a computerized system there to track where it goes. So they don't just put everything together. They're not supposed to put all the barrels together. So each cell or area should be compatible. So if you had an acid waste and a metal waste separate, you may want to also put them then separate in the landfill. So they're very careful about what goes into barrels. Now, UH, we've got hazardous waste people, and they, you know, what is in this? You know, I give them batteries. You know, so the batteries are acid and metal. They go one place versus my other waste. Okay, and this is similar to a regular landfill. It is covered daily, 1 foot thick. We don't want anything to get in there. But a lot of times, you know, obviously we're not going to have people down there touching stuff. It's hazardous waste. We use heavy trucks, so it has to be, the heavy equipment has to be able to go over it or next to the cells. You see some space in between the cells that you won't see at normal landfills, regular municipal landfills, that the trucks can put the barrels in along the sides of the cells. So operator safety obviously is an issue because what if something was in a barrel that wasn't marked right, it was reactive, and it wasn't marked reactive, could be a problem. The main problem people worry about is leachate. Because even if it's in barrels or required to be in barrels, they're going to break down. The metal will break down. We get leachate through it, we can have problems. So we're always going to be looking at the collection and monitoring of these sites. So although, you know, it seems like it's out of sight, out of mind, it still can be a liability issue. The most important thing is site selection. It's hard to get these sited now because of people. NIMBY, not in my backyard thing. I just saw that on somebody's T-shirt last night about that tank farm. They're now trying to move it out towards Limestone County. Colonial Pipeline.
Well, I keep seeing signs all over the
Well, they were going to put it out where we live, and we had, we had 2,000 people at one rally, okay? So they stopped that. Then they were going to put it through Huntsville somewhere. Of course, nobody would let that. And then it's going out west. I don't know why they don't use the right-of-way where we have the other pipeline or whatever, but they don't. In Alabama, they can put it anywhere they want as long as they give you fair market value for their land because it's utility. So in some states, it's not so. But in Alabama, they can just come in and say, I'm giving you $1,000, I'm coming for your land. But the people have just been going to the politicians, so we've been stopping it. So it's the same idea. Not in my backyard. Nobody wants it. But one thing about a site is you don't want a place that just goes directly to the groundwater. The good site, if you're having to site one, is aquitard, like very thick clay lining, natural clay, with no fissures or holes in it. So around here we've got clay, but we also have limestone. And we have a lot of cracks, and we have disappearing streams. So even North Alabama is not a good place to put any of these landfills because there's direct contact to our groundwater system. So you want to have redundancy. You want to have good natural conditions. You're going to look at the surface and subsurface hydrology. Okay, we don't want to have an aquifer directly, a drinking water aquifer directly downstream from this, because if it did leak, we're going to have a problem. Also, the surface hydrology. If it rains, where does the effluent go? We have the politics, as I said, not in my backyard. It's big. Also, is the transportation system big enough? We're going to have heavy trucks coming through, so if it's a small road, they're going to have to do something about it. So a lot of times, it used to be they would get stuck in areas that were poor people that couldn't get lawyers. You notice Triana in Alabama? Triana's got wastewater treatment plant and all kinds of stuff down there. The poor area. So they weren't fighting it. Whereas they could never go in Madison because people there would fight it, with lawyers. So you'll see that now we've got this kind of a justice thing going on. They won't let it go to poor neighborhoods anymore. So right now it's probably impossible to get another one. The transportation system would be important because the trucks have to bring it in. It has to be safe. Okay. The important things are, we know it's going to leak eventually. Everything leaks. Nothing's perfect, okay? So we look at the leachate, which we talked about before. We're going to have rain. We're going to put in some kind of filter zone, sometimes just soil that will filter it. But then we're going to have some kind of a collection system or a stopping system. It used to be you could just use clay and tamp it down. But you can't do that anymore. You've got to use probably layers, a few layers of liner, and then you've got to collect your leachate and treat it. Okay, and one of the things they use are geotextiles, geogrids, and of course we're going to collect that leachate. We're going to have a pumping system, a piping system. Well, that's what the nuclear waste people, that's why they like those areas. They like because it's dry. It's dry, so you don't have the surface water hydrology problems. But sand is a problem because as soon as it does rain, it goes straight through. There's no slowing down the rainwater. That's why they flood so quickly. So yeah, for surface water it's good, but there are other reasons not to. And they always try to do it on the tribal lands, on the Indian lands. They say we're going to have 100 jobs, and you put the nuclear waste there. So that's been a problem in the past. They take advantage of people. So the DOE wanted to do that salt cave, and I don't know whatever happened with that. Anyway, you need a primary layer, and then you usually use you have a secondary leachate controller, because something's going to get through all the time. And then your detection system, and then obviously your secondary barrier. And a lot of times then they'll put clay underneath that. So we're talking about, much more sophisticated than 20 years ago. So they're not cheap to put in, and the liability issue is great. That's called a composite system. So we can have composite liners, something that would absorb, activated carbons, absorber. Excuse me. Anyway, liners. Poisoned. If we're going to collect that leachate, what are we going to do with it? Okay, can we burn it off, flare it off? Like I said, methane you can do something. Sometimes they treat it. It's a liquid waste. They can treat it. They can have the incinerator on site. Different ways of going on there. Obviously, we said we got to cover it. So you can have the temporary cover and then the final cover. So there's ways, according to the law, that you're supposed to do all this. The one in Alabama is probably going to be going on for years because it's thousands of acres, so it might not be an issue. But you could never put anything on top of it. And we were talking about the golf course. On a municipal landfill, eventually you could put something recreational. But in these, you obviously wouldn't want to do anything. I mean, you're going to put the grass cover and everything. But I wouldn't even recommend putting trees or shrubs on this kind, because you never know what's going to happen. So there's long-term monitoring probably forever.
The root system could break something?
Yeah, because of big roots. Because, you know, tree roots can go 30, 40 feet. You want to be careful. And how can you control that, though, in 50 years? And there's always that, you know, despite these things. There are cover systems out there. Obviously, we're going to put grass or something on it. They put a filter on top, which seems weird, but you can put the filter on top to stop those from going down. You also look at drainage. On top, you have to have drainage. So you don't want the leachant to go in and become leachate. So try to get the water to go off the system. So if you had grass and you had soil underneath, you would have something to push the water off. And obviously, the long-term monitoring would be extremely important. There is a computer program EPA has called HELP, which you can design one. Okay, so you might, if you can look that up from the EPA site. That's the help model. But obviously, you got to look at mechanical compression. You know, you have to have the soil and stuff on top of it pushing down. Remember, we could have the leachate coming out, contaminated leachate. Obviously, things degrade. The barrels are definitely going to degrade. The liner system's not going to last forever. So you've got to put contingencies in there for all that. Raveling of the fabric. Also, I said surface water, so that can go off so it doesn't go through. So there's a lot of new stuff going out there because the materials are now coming out more. Geotextiles. I don't know if you went to that conference in Orlando. Did you see geotextiles? I can remember at different conferences picking them up, and they're coming out with all kinds of new things. So there's much more technology there. I'm not sure if they last longer. Oh, in Paris they had more, the water quality. That was a bigger conference. Well, anyway, if you go to conferences, you pick up on new technology because companies are trying to sell it, and they give you different things. But you always want to find out how it's been used because the long-term durability is extremely important on these. You're liable as the operator, but plus the people who gave you the waste are always liable forever under RCRA. So, you know, everybody's concerned. Obviously, we said we had geomembranes, geotextiles. We can use clays, and there's new clays out there, the geosynthetic, where they add stuff to the clay. You can use regular clay formations. One thing about clay, though, sometimes it does crack. In like ponds and stuff, you see cracking, so there can be natural problems with any of these. You can add mixtures, you know, like concrete, how we add things to it, mix things in for concrete. Anyway, like I said, there's tons of stuff. There's a table in the book, 13.2, which has got some different characteristics of different liners. Okay, the transport. We got transport, which we don't want. Transport's the bad thing. The risk problem is once it moves. We can transport through barriers, so our geotextile doesn't work. Okay, nothing works completely. And that can be through diffusion, either liquid or gas diffusion. Okay, and we said partitioning where things move, like the partition coefficient, the oxynol water coefficient, where things move apart, like oil and water come apart. You can have partitioning, and something might be detrimental to your barrier. So just because something's in there now doesn't mean it's going to remain as that as it degrades. So we can have problems with that. Clay, though, retards movement. Remember, retards slows it down. So clay is not totally impermeable, even compacted. So eventually things will get through, but it does retard it by like 1,000, 10,000 times. So it does slow it down. Hmm?
Is it the best?
No, but it's the natural and the cheapest, especially around here because we have so much clay. But now that they have to do a composite, though, they can be clay and then geomembrane and then the leachate and then above that another geomembrane. But so you've got 3 barriers. So the first 2, who knows, they may break down and the clay may be the last thing. And if that, you know, once it gets in the groundwater, then we're going to have a big cleanup. So we want to avoid it getting in groundwater. So if there's any way you can make a pressure that we can always pull out rather than having positive pressure pushing in, that's a really good idea, to have the negative pressure all the time. Okay? Stability can be a problem, as we said, when we close it in or when we have the heavy equipment on it. We have the outside forces. We have the earth itself, but we have materials such as trucks and things. Subsidence. You know how we have sinkholes around here? Because we have the limestone. You know, the big hole just dropped. It happened in the highway a couple of years ago. That could be an issue with limestone underneath. We have the nice clay liner. We have the triple system, but underneath we have limestone. Drops in. And it happens sometimes if you pump too much groundwater. The groundwater is buoyant, holding it up, and then somebody's pumping the groundwater and it drops down. Changes the environment, you know, just around the area changes. That can be detrimental. the stability. When we're putting in the cells, we have to make sure the sides are stable. Oh, by the way, don't ever go into a pit, a thin, what do you call it, pit by yourself to take a water sample. I just found one of my students went by himself with no gear. The sides collapsed in on him. He would have died, but a backhoe operator got to him within 5 minutes. It's actually against OSHA, but just, don't ever do anything alone. He graduated like 5 years ago. Yeah. So you can have all kinds of failures. So you just want to be careful. Surface impoundments. Okay, so we can put things like in the ground, landfilling, but we can also do it on top of the ground. And there are storage places that are like that. They're considered storage. They're not like final disposal, final destination. I just saw that movie. It was bizarre. Weird movie. So you'll see other things that are considered land applications, but they're not recommended. Because you put those barrels just sitting on the ground somewhere, and then they're going to leak, and then you've got the soil all contaminated and everything. So for temporary disposal on site, that's okay. But, we don't want to do it for long term.
Sometimes they build a bunker.
They build a bunker, and then they have containment, like concrete. It's usually not permanent. It's usually temporary. It's usually there's storage or there's disposal. Two different things. What are they calling them? Storage? They're probably calling them storage. Yeah, I heard that. But I think those are supposedly storage for legal reasons. Disposal is a higher thing. I don't think they're allowed. Well, I don't know. Maybe I'm wrong. Maybe they are. Enclosure. Radioactive, I heard. Why would they be there?
They were with the lab, and they had like these big tubs of lemon drops. And
What?
the environmental think they were getting from people because they were putting them in their offices and having like little dishes of lemon drops. And
Oh my God.
I heard they use those places for rendezvous.
I know that for a fact because, not like I know it for a fact,
You know,
but
you know.
I know some people that
Whoa,
got
Mary.
caught.
There are these
Like
ugly bunkers out there down by the river.
They got caught.
They got caught going into one of them. How'd they get into a bunker?
They got keys. You can check out the keys. Where I used to work at a propulsion lab.
And they check out the keys and they go there and have affairs. Well, that sounds real romantic.
That's what I did. And supposedly this one guy had a whole empty bunker set up with like a bed and all this stuff.
Did he
And
get
there's, like,
fired?
all kinds of nasty spiders and bugs in there.
Did he get fired though? I would
Yeah.
think he got. Anyway, yeah. Oh yeah, we got strange things here in Huntsville. I'm sure the DOE is like that. But when you close one of these sites, it's like a bathtub. Think about it. We put all these liners in, and it rains in it, and it all sits there, which is even worse. So you've got to pull out that leachate because it'll just break down everything if we get acids in there. And cover integrity is important because we don't want anything breaking through. We don't want kids playing there. We don't want people doing things like they do here at the Arsenal. Obviously, we want to look at the air because we're going to have gas. When things are degrading, we're going to have gas coming out. So there's a lot. I want to get to that with it. Lot to look at, but it's similar to regular landfill, but even tougher to site these and even more monitoring. So, do you want me to answer a question on 13, Mike?
No.
No, everybody wants to go. Gee. Okay, that's it, Jared. So no class at 26. Yeah, or email me.
I don't think I can do that by tomorrow.
Just pick two. Just pick two. And figure out which one you can get.
How should I get in touch with you Monday to get my paper?
I've already started going through it.